All right, good afternoon. Any questions? No questions? Okay, hearing none. So, today's topic is, do you have a question? You have a question?
Regarding CBS annotation.
Yes?
Um,
So, first question which we have is the type A
for
in
scalar continuous.
Yeah.
so what we thought was whatever value you want to call the continuation with,
That's correct.
that would be the type A, which
Yeah.
is basically the type of shift,
Yes?
right? But in the example which we have, the tree block.
Okay, let me. Um, this one?
No, in the continuations 4,
Okay.
slide 6.
All right.
So here, as we were discussing the other day, if we are trying to make B and C to 5, such that we are returning a 5,
Right.
then my A would still be a unit.
All right. So let me see. I did try that, and I put some traces on that on Piazza.
Yeah.
So um, so A's, yes, this continues to be a unit.
Yes.
Okay, let's see what this one was. Oh, plugging it in for those one. Okay. This is a mouse. All right, so so we're going to return the file where? Here.
Yes.
Okay, so then means the value of the shift that is this thing here now becomes.
No, this is C. When you return.
I'm going to tell you, it's going to have to be the same because
Yes. That would become
then this one becomes file.
Yes.
Then we have to return something here.
Yes.
This one stays in it.
Yes. So the confusion is when we do this, it returns an error saying the A should be file 2.
No.
Because even in your answer which you posted on Piazza, you said the way I fixed it was to add a null below the shift and change all the unit to file.
Okay, I guess I don't think I meant all of them. I didn't change this one.
Can we just try it?
Well, how about you put another question and I'll put the entire code on. I mean, I don't think that's a good use of class time to monkey around with it. But.
Also, the continuations 2's video is missing. If you could just upload it sometime.
Okay, I'll try if I have it actually. Okay. Did you put a request on Patsy? Okay, I see. I must have misread that one because I said didn't I upload it? But now I realize you said continuations too. Yeah, it might have been that it was another bad day. Okay, other questions? Yeah. So really, these kinds of questions are very hard to do in real time in class. It just burns up so much class time. I don't want to put those on Piazza now. I didn't want to post the entire code because I thought, it would do you some good to do the code on your own. But if it does more harm than good, I'll be glad to post it. All right, so concurrency utilities. So plain Java locks are low level and unpleasant and error prone. And we can't totally avoid concurrent programming. So what to do? And so the solution that kind of the Java story is that Java provides a bunch of concurrency utilities in Java util concurrent that are done by experts and that mere mortals can use. And if you use those utilities instead of doing your own locks and synchronization primitives, then you'll get good performance and you don't have to do any of this really tricky and tedious programming. So, and this is for some reason an advice that not that many people are heeding. So I talk to the people who do consulting for Oracle, and they go into companies where the people write this code, and they say there's all these people out there who use very low-level primitives. They'll use volatile. They'll use synchronized. They don't have any idea what they're doing, and they should really be using these concurrency utilities. There's this really nice book by Brian Guts, Concurrency in Practice. If you have to do this kind of stuff for a living, you should definitely go out and buy that book and read through it and heed its advice. And so he basically says, don't use the low-level primitives. There are very few people in the world who should be using that. Instead, use those utilities. And it says it's very unintuitive for people what happens. This whole issue of what the memory model is, the various caches, is not something that people really have a good idea about. And so the upshot of this is, we want to use what the pros put together. And just to put this in perspective, I'm showing a little bit of code here that was done by well-meaning amateurs, and we'll see what's wrong with it. So first of all, you've seen how we did the bank account last time, and then we added some synchronized methods, some locking, and out of that we made the methods thread sync. We made sure that every operation called acquired the lock first, then did its thing, then it released the lock. And out of that, you would get a bank account or a bank in the second example, that every one of the methods was protected. One thread would go in, the other threads would have to wait, only one thread would access the thing at the same time. So they've done that with a bunch of the collections that have been in Java forever. For example, vector has been in Java since Java 1.0, and the methods add, remove, index off, and so on they use that very primitive synchronized notation, but it's acquiring the lock when you call add, relinquishing it when that call returns. The same thing with remove, index off, and so on. So now I want to implement a method, put if absent, that adds something into a vector. In this case, it's a shopping cart, a vector of items. I want to add it in there if it's not already present. So let's see what I'm doing here. So I'm acquiring this lock. I am checking whether the thing is present. And if it's not present, then index off returns -1. In that case, I added. And finally, I unlock. What's wrong?
You said you should use while, not if. In the try.
That is true. I'm sorry? Okay, where do I have? guess that should be items, right? We'll call it elements too. So I understand what you're saying with the while, and that would be true if in fact this method called wait. Or await, I guess it is, if it called await, because in that case it would get kicked out. But I'm not getting kicked out. I'm simply saying if it's already present, then I'm not going to add it. I'm not trying to wait until it is absent. I'm simply saying if it's absent, I add it. If it's not absent, I continue. And I'm not staying inside the protected area. I'm just saying if it doesn't work, I just simply don't do it. Or in this case, I don't have to do it anymore because it's already present.
Does this thing log the entire vector?
What am I locking anyway?
You are locking when you call method that
Put
particular
in
method.
absent locking the method.
So you put it. What am I locking?
You have to lock the vector.
What am I locking?
The reentry as well.
No, the
Yes.
log.
Yes, I'm locking the enter block. Very good. Right, I'm locking part lock. Right.
So what is the reentry?
But it's a lock for this object, right?
Right.
So you're locking for this this instance of shopping cart.
Right.
So if there are multiple instances,
Each of them has their own lock. That's fine.
uh,
Because this thing is a val. It's a data method.
each thing will have its own shopping cart, right?
So if I have 5 shopping carts, each of them is going to have its own lock, and that's the way it should be. That way, if I were different threads operate on different shopping carts, then they can all proceed with each their own shopping cart. But if 2 threads share the same shopping cart, and they both call the put if absent method, then all is well. Because then the first one that wins acquiring the lock is going to be able to proceed with this.
Should we cartlog.log be inside the
No. In this case, I don't think it makes a difference. Because it can't throw an exception. But generally, we put these things outside the try block because if something like this can throw an exception, then the lock has not yet been locked. Only when this method call returns do we know that the lock has been locked. And so only then do we want to unconditionally unlock it later.
So we are only checking the item x at index 0, and then if it's not present, you add it.
Yeah. The 0 means start looking at index 0. That's a weird and ancient API.
Can this be injected, the if statement and the add statement?
Okay, so could another thread
Right.
at the same interfere with this thing? Could another thread gain access to elements?
When you say elements dot index of, is it looking in the entire shopping cart?
Yes,
So it's a for loop. It's going.
it's a loop. Yes, it's a loop.
So yeah, it's the same 2 threads, but the lock won't be.
So could another thread access this array elements? That's the question.
It won't because that thing is locked, right?
So it certainly cannot do it in the put if absent method. Can it gain access in some other way?
But in some other method, yes. It
How?
can go add in some other method if there is no lock.
Well, how? But it's a vector, isn't a vector thread safe?
There's nothing wrong.
All right. So first of all, notice that val is it's a public val. So that means that anyone who has a reference to the shopping cart can call cart dot. I guess that's element. I'm going to have to fix that so that's So it's publicly accessible, and what can I do with it?
You can add elements.
And I could add another element,
Right.
right? And so because it's publicly available, it has nothing to do with the card block. But of course it has its own block. It's a vector, and vectors are thread safe, aren't they? And so it's important to understand what it means that vectors are thread safe. That means that the internal organization of the vector, vector has an array inside, it has a length value, it has some indexes. The internal organization of the vector can never be corrupted. That's what it means for the vector to be thread safe. But that doesn't help us at all, because over here we are asking for something, for some invariant that has nothing to do with the internal structure that we are posing in addition to the internal structure. And so for that we would have to come up with our own mechanism. So the way to do that would be to make this thing private, and to make sure that any other access to the vector is also controlled by this lock and not by the vector's lock. Once we do that, we don't even need the vector anymore, we can just make it an array list. So the moral of this is that people often use a concurrent structure such as a vector because they read the documentation and it says this is a thread-safe structure, and they think thread-safe equals good. And that is just not so. Thread-safe means that the vector takes care of itself, in that rugged, self-reliant American way. It makes sure that itself is in good shape. The rest of the world, who cares? So vector is selfishly protects itself, but it's not good enough if you need to have other invariants, like in this case, that for whatever reason an item should only be in there once. And so it's hard. All right. So, so you should avoid vectors and so on. And nevertheless, when you look at the standard library, particularly the pre-Java 5 library, there's all sorts of stuff in there that supposedly you should be able to use to stay safe. So what they tell you is, what you should have done is, you should have synchronized not on that other lock, but you should have synchronized on the intrinsic lock of the vector. And that would have worked. In this case, if some other piece of the code would have called add or remove, that would have also tried to get the intrinsic lock. And so by surrounding this, which you want to be atomic, with the intrinsic lock, will work. So, so should you do that? And the answer is still no. The next mistake that people make is, when you want to iterate over a vector, I'm getting an iterator here, and then I want to iterate. Of course, the iteration also needs to be protected by a lock, because as iterating is a pretty dangerous thing. You move some some position across, and so the iterator points at something inside your data structure. Now say that someone else adds to the vector grows to twice its size. Now the thing maybe still now points to the old one. So that would be bad. So you want to lock the whole thing. So here I'm locking the whole thing. See, now I'm synchronizing here, and while the iterator has the next one, I print the next one. What's wrong?
You're not still using the intrinsic lock, right? Because it's
Very good. So I'm synchronizing on what? I'm synchronizing on the iterator object. I'm not synchronizing on the intrinsic lock of the vector. This makes absolutely no sense. Why does it even compile?
the syntax is rich.
Because in Java, every object can be used as a lock. And so the iterator, even though it makes no sense to synchronize on it, can be used as a lock, and so the compiler can't find this. This is a surprisingly common error, actually, in published code. And so what happens here is there are all of these things that you could lock on, and people just get plainly confused. So you really want to be in a situation where you don't lock. You're going to get it wrong. So the people who designed Java utility concurrent then said, we're going to come up with a bunch of data structures, from some fairly simple ones to some pretty complicated ones, that you should be able to use without ever using synchronized, without ever acquiring or releasing any locks. They should be intrinsically safe, and they should have the kinds of operations that you need. So things like put if absent, and the kind of these common operations that should be there so that you shouldn't have to implement any of them. If you find yourself trying to implement some of these operations and trying to add some locking to it, then that means that you're on the wrong track, and you should instead be looking for a different data structure to solve your problem. So you should try to forget everything that you had in concurrency 1 and instead use these structures. That's the pitch that they have. And it does actually work surprisingly well. So the first data structure that they give you is the humble blocking queue. And it's a wonderful data structure. If I have nothing else to control concurrency, give me blocking queues. I can do a lot of stuff with blocking queues. And the reason for that is that, so here I have my blocking queue. And yeah, it's just a boring queue. You put stuff on the one end, and you take it off from the other end, and the queue is safe, that these operations never destroy the internal links inside the queue. And but it's very simple. You could implement a thing like this very easily, and there doesn't seem to be anything to it. So what's the use? Suppose that I have some amount of work that I need to do. So what's common is I have a bunch of threads that produce some intermediate result, and then I have some other threads that produce it, that consume that and refine it further, and maybe produce yet another set of intermediate results. And by putting those intermediate results on a queue, something wonderful happens. Thread number 1 grabs some amount of stuff, puts it on the queue, and then it no longer owns it. Then it goes on and does something different. A little bit later, thread number 2 comes and pulls that data item off the queue, and now the ownership has been cleanly transferred from one thread to the other, and you don't have two threads that operate on the same data item. So if you can organize your code that each thread owns its data item, it doesn't share it with anyone else, and then when it's done with it, then it puts it on a queue, thereby loses ownership, and then someone else picks it up from there. You can avoid all of that shared memory hassle. Now, sometimes that's a little difficult to do depending on the nature of the problem. It works best where the processing is isolated from each other. Like for image manipulation, let's say you need to transform parts of an image. Then every thread can grab a region from the image, can transform it, and then can put the transformed region on a queue, and then later some other thread could pull them off and stitch them all back together. There's usually some stuff at the boundaries that needs to be done, so that thread probably has to deal with the boundaries. But that's not so bad, because if you have a big image, and now you can chop it up like that. Now, these things might be expensive, but the boundaries themselves are, a single thread could deal with all of the boundaries. So that's a good way of dividing labor. The other beauty of the queue is you can make the queue bounded. You can say it should be at most n. And now something else beautiful happens. Oftentimes when you divide up the labor among threads, it's difficult in advance to predict exactly which threads are going to be doing work faster than others. And if you misjudge it, what then can happen is that some of the threads, they're done very quickly, and then they build up some enormous intermediate results, much faster than the consuming threads can ever consume it. And so that means that you're going to build up a large amount of intermediate memory. And it also means that those first threads here, they're going to all be pretty idle. And then you might have some poor little threads here that have to clean up all of this big fat mess. And it would be better if the first threads worked a little bit slower, thereby giving more time for these other threads that need to clean up with it. When you make your queue so that after it grows to some size, say 10 for the sake of the argument, that it simply stops accepting other work, then the threads that want to produce get blocked. They call put. The put fails because the queue is full. They block. And that means that they can't then go on and do even more work. They're temporarily blocked. And so you get an automatic kind of load balancing out of these keys. So safe transfer of ownership, automatic load balancing, what's not to like? Very simple data structure. And so if you have this kind of work that simply needs to be parallelized and coordinated, blocking queues are the way to go. And so notice that the little bit of locking that's involved here, the queue takes care of, and it simply directs your algorithm into a productive one. Next thing that's a useful concept. When you first learn about threads, you hear that there's multitasking in an operating system, of course. Multitasking means that the operating system will switch from one task to another, and they tell you that tasks they're very safe because they own their entire memory and stuff. But to switch from one task to another is really expensive. There's a whole bunch of data structures that need to be swapped out somewhere, and so a task switch is not something that should happen many times a millisecond. It's something that should happen once in a while. And so they say thread, there's a much cheaper way of doing it. The threads, they share the memory. Yes, you then have danger, namely multiple threads can corrupt each other's memory, but it's so cheap. But it turns out that nowadays, thread creation is pretty expensive compared to all these other things that you want to do. And it always goes like that. The processor outruns even things like thread creation. And so people don't like to create a million threads. There's the data structures that need to be managed. It's not free. What if you have something that naturally splits up into a million tasks? Then you'd have to have some way of grouping those tasks and mapping them to the same thread. And so it turns out that that's so common that one kind of wants to automate that. So for example, in a web server, that's kind of the traditional thing where it's so easy to say that every incoming request should kind of be its own thread. And then you might say, well, what if you want to transform an image? Maybe every scan line or every 10 scan lines you want to map to their own thread or something. And it's easy to get lots of threads. So the solution to that is to use a thread pool that matches tasks to threads. And so that's what you really always want to do. You want to say threads are kind of an implementation thing. And if you think about it, let's say I have a dual core processor in here. Yeah, here, two processors. How many threads should I run to maximally take advantage of my cores? 2, right? If I run 2 threads in parallel, that's the optimum. So creating 1,000 threads doesn't really do me any good. Right? 998 of them are going to be idle, and shifting them in and out is going to be some amount of work. And it's work that someone else should do. So when you use one of these thread pools, they map tasks to threads. When a task is idle, then it gets replaced by something else. And so that's really what we want to do. So I started out with threads because the syntax for it was easy, but you really always want to use one of these pools. So you make a pool with this thing. You can also make a new fixed thread pool. It's not a bad idea to make a fixed thread pool that you initialize with as many threads as you have processors available.
Is this Scala specific or
Java. This is all Java.
is Java not there?
Yes. So all of this stuff is Java 5. I'm just using Scala syntax so that you don't also have to learn Java syntax. But this is all in Java util compiler. And so next time we'll talk about Scala-specific stuff. But all of this is pure old Java. But even when I write Scala programs, which I tend to do nowadays more often than Java programs, I still oftentimes use these. They're very, very handy. They're fairly easy to understand, and obviously they work. That's an advantage of using a JVM language.
So how does this lightweight?
Well, this way you can create 1,000 tasks, 1,000 runnables, because a runnable has nothing. A runnable is just an object with a run method. And then whenever the runnable...
Wherein the thread is empty, the task is empty.
That's right. So when the thread has nothing else to do because it has finished a previous runnable, and it can tell because the previous runnable method, the previous run method returned, then it says, oh, run method returned, time to start another one. So it simply does them one after another. So this works really well for tasks that do one thing and then are done. So finally, then there is a way of using these. You can have multiple pools, and that's often very handy. What you can put a bunch of tasks on a pool, and then you can shut down the pool, and then you can say, I want to wait until the last task in this pool has been finished, and that way you know that your entire job is finished. So it gives you a way. That's often the most difficult part in one of these algorithms is to know when you're done, because you're going to distribute the work over 1,000 different workers. They all go and do their things and give it to other workers. How do you know when you're actually ready to harvest the result? And so putting them all in a pool is kind of nice because the pool can tell you. So we've seen runnables. Runnables are things that just run. A callable is an extension of a runnable. Instead of having a run method, it has a call method that returns a value. It returns an answer. So anytime that you want to compute something that gives you a value, could be a number, could be a string, could be some object of more complicated structure, it makes some sense to make it into a callable. Then when you give the callable to the executor, then right away you get something back. You get an object of type future. And that future is an object that you can carry with you. And you can once in a while ask it, hey, are you already ready? Can I know what the answer is? And eventually it'll tell you, yes, I'm ready. So over here, I'm making a blocking call to get. Now the blocking call to get is of course a little uncomfortable because usually you have a whole bunch of futures in your pocket. And so you want to know when they're all done. And so the best way of doing that is to use this executor completion service here. You ask an executor for this completion service. You submit a bunch of tasks. You get back these futures. And then you could deal with the futures, but what you can do here, but that's so much nicer, is the completion service will hand you every task as it gets completed. So when you call service.take, that blocks, but as soon as one of them is ready, you get the first one that's ready, and then you can get its answer and process it further. So this one here, it delivers them in the order of completion. And so this is a very nice way of doing processing. You parallelize your task, you give it to the service, you then get them back as they come back completed, and then you can do whatever else you need to now do with those results, and usually hand them off to some other task. And this giving them back in the order of completion, you could implement that yourself, but you really wouldn't want to. So this is a nice and useful service that you get. Finally, every once in a while it happens that you have some itty-bitty thing that you need to manipulate, an integer or a Boolean typically, where multiple threads update the thing. And yes, you could figure out how to do the locking and whatever, but you may say it's just tedious, you don't really want to do it. And or you might be considerable the expense, but it's usually the tedium that we're concerned about. And so for these very simple data items, they give you these safe structures, these what's called these atomic structures. So like for a counter, let's say you need a shared counter. Sometimes you just do need a shared counter. You just make it as an atomic integer, and then there's an operation called increment and get that safely increments and gets the result. And then you can simply use it. There's a all I've ever used in my life is atomic integer, atomic Boolean, but I guess some people would use these others. There's a few thread safe collections. So I said, vector doesn't really cut it. And the big problem with vector is it's not that vector is inherently evil, it's just that it's missing some important operations. The one thing that I use all the time is concurrent hashing. So it's very common you have a bunch of threads that want to deliver work into some common result area, and a concurrent hash map works fine. It's a map. Concurrent means that it's safe for multiple threads to insert and remove things. It has useful operations such as put if absent. And it's also implemented in a kind of clever way. If you were to implement a concurrent hash map, You might say, well, I'll have a lock, and only one thread can put something into the map at the same time. But if you have lots of threads that all compete for that one map, and they all exclusively lock the thing, it's not so efficient. What the concurrent hash map in the Java implementation does is it says, well, what's a hash map? It's you have an array of linked lists. And if one thread mucks in this linked list and another one mucks in the linked list over here, that can happen concurrently. They're not in each other's way. So they very cleverly lock parts of the data structure. Don't try this at home. Right? This is obviously a very dangerous thing to do, and if you're not carefully debugging exactly what you're doing, that bad things are going to happen. So this is definitely something where you want to use a data structure that's some expertise. There is so for almost everything that I've ever had to do, the concurrent hash map works great. If you, for whatever reason, do you need an array, there's this thing called the copy on write array that has good concurrency characteristics for arrays, and you might need one so. So, in this lab here, so at this point, I guess all of you will have a multi-core machine, but I did have a couple of students last time who didn't. So, let's look at this program here. So here's this recursive process directory thing that you've seen in various incarnations many times. It takes a function, it iterates through all of the directories and recursively visits when they again directories, and otherwise if it's a file, then it passes on the file to visit. What I want to find out here is I want to find the 10 most common identifiers in a set of files. So let's see what my visiting is. So my visitor is this function process. Process is now applied to each file. What does process do is it opens up the file and it simply reads the file, turns it into a string. This is pretty nice and easy to do in Scala. So now I have the entire contents of the file in one long string. Then I apply this regular expression to find everything that matches this regular expression. And I'll say that's an identifier. Then over here, I call get or else on this map. Why get or else? The very first time that I want to increment a counter. And the very first time when it's not yet in there, then I'll get 0 out of it. And otherwise, I'll get the previous counter out of it. And then I add 1 to it. So I either get 0 plus 1 or the previous value plus 1. And then I stuff that bit back in. So this one here will increment it. And later on, I just take this thing, I sort it. It must be an easier way of doing it. But here, I'm sorting it in reverse order. That's what I'm doing. And then I'm taking the 10 most frequent and I print them up. Now in a when you run this as a single-threaded program, this is just fine. When you run it multi-threaded, you're going to be seeing pretty soon that things are going to go wrong because then you have multiple threads accessing this shared structure. So that's the purpose of the lab, to look into that. All right, let's go for it.